Now if we look at a pendulum, string, a weight, center mass maybe at the center of the weight, kind of like the washer that we just saw. The string is typically at an angle unless the washer happens to be at its central equilibrium position, the position where it would ordinarily just hang by itself. That's represented by this dotted line, that position. But typically the washer will be at a position that's described by its displacement x in the horizontal direction from its equilibrium position. Now the displacement isn't all horizontal. As you know, if the string maintains a consistent length, the pendulum is going to follow the arc of a circle. But if the displacement x is small compared to L, then that arc of a circle will be almost a straight line. The pendulum won't be very high at all above its equilibrium position, and most of the displacement is in the x direction. And what we're going to be concerned with here exclusively is small oscillations of the pendulum, small displacements. Now when the pendulum is at distance x, what forces are acting on it? Well, there's a weight force acting straight down, obviously, and of course that's parallel to the equilibrium orientation of the string, straight up and down here. And there's a tension in the string. And those are the only two things that act in this washer. Nothing else is touching it. Of course, we're ignoring air resistance. So we have a tension parallel to the string and a weight straight down. Now, these forces can't possibly be in equilibrium because the tension force is not parallel to the weight force. They can't be equal and opposite. They're not in the same direction. And it should be obvious that the resultant of a force in this direction and a force in this direction will have at least a component in this direction. So we draw the following force, or the force diagram that we see here with tension here and weight here. Now for small angle approximation, if this angle here is small, that is if there's not much deflection, if x is small compared with L, then there are several things that we can do. We can say that to the extent that the angle is small, we're in y equilibrium. Because if the angle is small, remember that the pendulum is actually following the arc of a circle, but there's not much y component to the displacement along that arc. So we're going to make the approximation that we're in y equilibrium. And that therefore the net force accelerating the pendulum is in the x direction. Again, the smaller the angle, the better that approximation holds. Now if that approximation holds, the y component of the tension is equal to the magnitude of the tension. Okay, so we have the tension here. It's got a y component that's approximately equal to the magnitude. There's not much difference between the tension that we get, the y component that we get by projecting straight over to the y-axis, and the tension. The difference, the factor, is the cosine of this angle, and for small angles the cosine is very close to 1. These assumptions, all the assumptions we're making here, are all good to within 0.5% if x is less than 1/10 the length of the pendulum. That is, if the pendulum is displaced less than 1/10 of its length from equilibrium. Now when that is the case, we can summarize what we have by this diagram here. We have the tension in the string that's just about equal to the y component. Since we have y equilibrium, the y component of the tension is equal to the weight, so we say that the y component is approximately equal to the weight. Well, it's equal to the, well, yeah, it's approximately equal because this is an approximation because we don't really quite have y equilibrium, but we're so close that it doesn't matter much. The tension then is approximately equal to the y component of the tension. That is, there's not much difference in the length of this vector and the length of this vector for a small angle. So we're going to say that the magnitude of the tension is approximately equal to the weight. And the x component of the tension is going to be the net force on the object. So that we need to find an expression for this x component. And we can do that fairly easily. We draw these two pictures. Here's the tension with its x component and a projection line down here making a right angle with the x component. And here's a picture of the actual string and the x displacement and the equilibrium position of the pendulum. And of course there's a right angle here because the equilibrium position of the pendulum is vertical. Okay? These two triangles are therefore similar, which means that the ratio of Tx to T is the same as the ratio of x to L. Okay? The sides are in the same ratio. So we say Tx over T equals x over L, and now we can solve this for Tx, I'm sorry, and we get Tx equals T times x over L. Remember that the tension is approximately equal to the weight, so that's approximately equal to the weight times x over L. So now we see what the restoring force is for the pendulum. The force that tends to restore it back toward its equilibrium position is equal to its weight times x over L. And x over L is just the proportionality between its displacement from equilibrium and its length. As long as x over L is small, this is a very good approximation to this restoring force.